Okay. Even as Cameron's walking off. So this is, this is Coffee Compiler Club. I say this little thing at the start of every meeting. This is just, open mic questions about discussion about language implementation, compilers, garbage collection, save points, semantic versioning from last go around, whatever. I record them. I put them up on YouTube video an hour or two after recording. If you don't like that, bail out. It's an open mic. I ask you mute if you're not otherwise speaking so that we don't get background noise from a dozen people. And I myself will be doing maintenance as people dribble in probably for the next 5 or 10 minutes. And after that, like I said, I have no particular agenda, although we went round and round on save points and semantic versioning last go around. And already in chat, here it is. We'll say something about it because I haven't read it. Scheme. What are you doing with scheme? Gradual typing for functional languages. Yeah, that's what I'm doing.
I thought you might like it.
Oh, but it's all got this, the actual semantics. I'm not doing, I'm experimenting, so I'm not trying to write any, actual typing systems in the formal theory. But I do have a strange, I can gradually type every kind of error on the planet. As well as, all the non-errors and all the states in between. But that's the thing that's kind of like, what the hell am I doing here? I've been writing larger snippets now, and they're kind of interesting. Weasel hat, what to define? Okay, maybe this is more readable. This is a recent paper. Oh, I see.
Yeah, that's how I found the link to the first one.
Right. Yes, so I do control in the type. So the typing algorithm is like the same algorithm that you use for constant propagation, given a sufficiently robust lattice, supports every possible thing on the planet that you can make everyone look like a nail, and you have this giant hammer. So I do constant propagation, conditional constant propagation. I do liveness, which is reverse flow, in parallel in conjunction with forward flow, in the optimistic way, so that I can take use of the facts of something simultaneously live and or constants in a way that you can't get by running liveness and constant propagation back to back an infinite number of times. And I do call graph discovery. So first-class functional languages, first-class functional pointers are tracked precisely. There are a bunch more people floating in, and here I am yakking. Let me go do things. Like 15 other things that you hear about from the functional language community and or classic compiler community, I'm all doing essentially all at the same time. Somebody else say something, because I'm going to be busy for a second here. I just got a flood of people.
I saw the recording from last week, and it was actually a subject I was working on as well with GC stack walking. And I was wondering if I was wondering about what the actual ABI is for hotspot compiled methods. There's some comment somewhere in the source code that says it's just the CABI shifted by one register. So in the first register, you can put the JNI environment and then do a native call. But that doesn't seem to be the entire part of the story or the entire story, because it doesn't say anything about which registers are volatile. And when I say volatile, I mean which registers can be assumed to be clobbered when you do an out-of-line call. So they should be saved by the caller. Because
the calling convention is specified in the AD file, and there's a list near the top somewhere that says caller and callee save registers. It's just for standard out-of-line call. All the intrinsics claim they clobber what they clobber locally on the intrinsic description, and then internally they have to save and restore registers to match that.
I see. So the intrinsic, it's up to any intrinsic to save and restore registers.
Yeah, intrinsics typically have a set of input registers and a set of output registers, and they don't have to be, there can be multiple inputs and multiple outputs like div mod. And they don't, I think, and this may have changed, but I don't think they list a set of clobbered registers. And therefore you have to save and restore if you're gonna clobber. And you're running it as an intrinsic, as opposed to running as a standard call, which includes all safe points and GC points, where you take the standard calling convention.
Yeah, so the case I ran into was that I was doing just a normal call node, but then there was an OOP map attached to that said RBX held an OOP, and RBX is a volatile register on the CABI. So I expected the register allocator to generate spill code for this in the caller, but apparently the callee is responsible for saving that value somewhere, because it then goes look code, the GC code goes and looks in a register map structure that is filled in from information from the caller frame. And in my case, this was missing, so this caused problems, but this was kind of surprising.
Bug tracking in these things is always a nightmare. To
Yeah.
use all the blah, blah, blah lot flags here and make these things happen lots more often, and you generally get faster, quicker crashes. But so someone's unhappy about EVP, which is not any special register in any particular way. Yeah, you've failed to declare one way or the other that it's caller or callee saves. If you go to a deopt point, there is no restore because deopts jump to the interpreter and never come back. But if you're going to a classic safe point where it's just a call out and call back, somebody has to save and restore it, and that's usually declared in the calling convention, which, you can make a build that's got a different calling convention that does EVP or doesn't. Different people do it different ways. And for a while, we ran different conventions on, some Linux version versus x86 Solaris versus Windows. I don't know what the state of the current world there is.
Yeah,
there's also a different convention for 32-bit x86 versus 64. That was a mess, but that just turned into, if-defs around the calling convention description files.
There's currently still two AD files for 64-bit and 32-bit x86.
Yeah.
So there might be still some differences. I have to maybe look in a little bit deeper into the AD files. It's interesting that they chose a DSL for this.
I can tell you the history of that because I was there. I was part and parcel.
Yeah. For somebody coming into this, it's kind of frustrating because my IDE doesn't work. Why isn't it just C++ and some good API?
Yes. So I hired a friend from grad school with me who had been working at TI, and TI flipped new chips, every other week, twice a month. And they would custom chips for every kind of auto manufacturing on the planet. And, at that time, automobiles had, even then, 20, 30 different CPUs in them. It was insane. So TI had this pattern worked out with this AD file-like thing that they could edit and modify a little bit and have a new backend, flip the DSL and then get a new backend the next day. So we were going to do this DSL, and some pieces of the DSL were kind of slick and helped, and some pieces totally sucked, and I would never do that DSL again. But at that time, I had a guy expert in a company that was doing multiple backends, and we were supposed to be highly portable, so we were going to do multiple backends, which Hotspot did and went all kinds of places. So we took, basically his experience from TI and implemented it right then and there. That being said, like I said, I would never do that again. Some pieces of that were really slick because that's what a DSL is for, and some pieces really sucked, and the suck parts I wouldn't pay that price again. So meanwhile, here we are 20 years later, and there's a DSL there. The DSL is a little obnoxious because it's itself based on technology that was old at the time we picked it up. So it's a little clunky. and like I said, does some things super well, including register file descriptors look clunky and weird, but they just exactly hit the shit you need. And some things really suck, including the indirection between, you know, what you want and what you have to write. And go read that AD file and what the hell is this thing doing?
What project are you working on, Jordan?
Just OpenJDK. I'm working on Project Panama, so basically we have dynamic binding of native methods, and it's a slightly different interface than JNI, so you can pass object handles down into native code, which simplifies a few things as well. And I was looking into intrinsifying calls for this. Yeah, and running into bugs along the way because I'm not a VM engineer and trying to figure it out anyways. So yeah, it's been an adventure.
If you're intrinsifying, then you probably are not taking the normal calling convention. And if you blow an intrinsics calling convention, then later code in the JIT can totally screw up OOP maps because they're confused as to who's an OOP and who's not.
Yeah, so there's two pieces of code in the GC I saw. One looks at the OOP map that's stored at the return address for the call. That's the one that's failing. For the other one, because we don't pass any OOPs, I can just skip that for saving the arguments for the callee. And I'm borrowing the calling convention from C, which should work, but it still has OOP maps there for registers that should be destroyed by the callee.
Well,
so
the
I'm
OOP map's going to cover everything, but it should list who's alive with an OOP and who's not. And separately, it lists who's clobbered and who's not, because that goes to who gets saved.
Yeah.
I changed all that shit at Azul. There's a better way to do that now.
Yeah, I'm still figuring it out, but currently I have a test case where there's an OOP map at the return address that says, oh, there's an OOP in RBX, which is should be a clobbered register, and then it tries to find it in the callee frame. So,
well, it can still be clobbered register and also be an OOP. If the expectation is the callee is going to use the OOP and then throw it away.
Yeah, but there's no OOPs being passed down. So yeah. This should be an OOP that's alive at the point of the call. And I'd expect the caller to be generating code for saving this.
So if you have a test case in hand and that it's simple, then you're done. If you have a test case in hand that's really annoyingly hard to deal with, ponder throwing on like safe point a lot, excomp, let's compile everything, and safe point a lot, and GC a lot. They all have binary search flags as well. And see if you can't get yourself a test case that's super simple and comes up really fast.
Yeah, I have one that's really fast. It's just a benchmark that does an upcall and then that hits a save point somewhere along there and starts walking back, and it jumps from the entry frame back to the entry point into native, and then there's missing values.
You've called into native and then back into JVM.
Yeah.
And you're unwinding. That's a more complicated case, but it shouldn't. Who's saving it? You're talking about calling from you're failing from the call from native code into the JIT code, or failing from the JIT into the native? Which transition?
Yeah, JIT into native. So there's a compiled frame, a C2 compiled frame that has one of my native call nodes in it, so native call, and then that goes later on back into an upcall. And then that hits a save point, and that triggers the GC stack walking.
Yeah.
Yeah. And then, yeah.
Yeah. But if you're doing a native call, you should look at the native call convention as specified in the AD file too.
Okay.
There's a JIT to JIT convention, and there's a JIT to native convention. Because like JIT to JIT can do floating point registers, but JIT to C code, for the longest time couldn't pass floating point args and floating point registers because it screwed up var args and printf. So floating point args are passed in the integer registers for the stack. And so I skipped that with the AD file hack. So that one depends on what CABI you end up calling to, but there is a native ABI description But that's an AD file. And if you just clone that, I don't know why that would be busted. But somehow you've edited or you've added a native call.
Yeah.
And got the
I've tried a few quick fixes, but I feel like I just need to sit down with somebody.
I'm certain it's a one-line fix, probably even a
Yeah.
one-character fix, but it's a subtle one.
Yeah.
Somewhere in the AD file / wherever you've been hacking, there's a one-liner that says, and also, this is your calling convention, and you don't have the right one somewhere. Sorry, can't.
Yeah.
That's all I can do remotely here. I haven't looked at this code in 20 years anyhow.
Fine. It's just what I've been up to. So I was wondering if anybody ever had to design an ABI, and specifically, how do you determine the set of caller and callee saved registers?
Oh, I can tell you how that one goes too. That's a design of an API, as opposed to, here's another person, as opposed to implementing it.
Have you designed an ABI?
Me? Bajillion. It goes with every compiler on the planet. If you're writing code to anything that's not got an ABI already to spec, you write one. And if you're writing something to ABI spec and you're cursing and swearing and wondering why, you go read up the motivations and you discover that that there's a done this way for this reason. So a lot of this shit like makes no sense now, other than to have a rigorous thing that we all agree on. But back in the day, it was all about, caller versus callee, and who did the saves and who did the restores, and making use of extra registers at the leaf of a calling. Your call execution goes up and down the stack, but you used to spend most of your time in the leaves. And after JITting in Java, that's also still true. You're in and out of the leaf calls a lot. So if the leaf calls can agree to use different sets of registers from the higher up the stack, then no one has to save and restore. So as you're working your way down the stack endlessly, what this guy saves and you want to use, the next guy's not saving, so you have to save it, and he saves what he saves, and there's no savings here. Everyone's handshaking and storing and reloading and storing and reloading all the way down. When you get to the leaf, the one guy says, I want to have alive across this random call some set of things I don't have to save and restore. The called function is small, it's a leaf, and he says, I would like some registers to work with, but I won't touch the rest. And then no one has to save and restore on either side of the call. We all magically hit the right place of interleaving, and you save the loads and stores in and out of the stack. Okay, that was the savings motivation back in the day when compilers were young and hardware was young. In most modern processors, that cost is low, multiplied by it's really freaking frequent. So it still kind of matters. It's all cache hits, it's all L1, L2, cache hits both ways, but loads and stores penalize all modern processors because of ordering rules, and so they don't get to go super fast and super in parallel. So having a decent calling convention is still worth some interesting fractional speed up. It's no longer the make or break that it used to be, but it's definitely still interesting.
What have you seen lately, considering that Intel now has more than 4 registers?
Oh, they can't change their convention. And they flipped it when they went to 64 bits, but they can't change it again because there's too much code.
Who's they?
Intel.
No, but I'm saying internally.
Oh, I don't know that anyone hacked the AD files at Oracle.
No, but I'm saying, have you seen any work in that area?
Oh, any like academic work?
Academic, LLVM, I don't know, pick something.
No, this is like, as a register allocation is like a done field, and it's not. There's still big gains to be had, but it's a done field that I've seen. I've not seen anyone do. Like register allocation PhDs come around at most once a year now. It's probably not true, but I've only seen at most once a year. Really rare. And we put into the AD file and the surrounding code support for register windows. Spark had windows, Azul Systems had windows, Itanium had windows. That was sort of the major other thing that was a way of doing support here. Other than that, no. It's like, you know, and then the other piece that I've talked about a lot is I made the register allocator very robust in the case of overspilling. So the cost of inlining or failing to inline was the same either way. Because if you failed to inline, you took call or callee save overheads. And if you did inline, but you inlined too much and you spilled, you took some spill costs. Those costs became equivalent with a lot of effort. Because they're equivalent, I was willing to over inline, and that was part of the performance story. Fine. Last 20 years, I've literally seen a handful of register allocation papers come by. So no, I don't think there's much going on here. And like I said, the dramatic costs have dropped as long as you can do some amount of load and store hits. Like you have a L0, like a store buffer on an x86 is almost an L0. Yes, and there are alternative conventions that everyone has to agree to. Yeah, so on the chat here. And the deal with that one is everyone has to agree to it. So you can't go grab the 1,020 years of x86 libraries and just pick them up and run because they'll use the standard convention from 20 years ago. But if you're willing to recompile everybody with a better convention, you can totally do that. And you know, it works. The JIT, the Sun Oracle hotspot JIT, I hacked that so you could have separate conventions from the JIT calling JIT versus JIT calling native because of the clunkiness of the native convention, which had all this history involving varargs, which I already mentioned. So, you know, I have a different convention in there and it's JIT to JIT, so you can just tweak it in one spot and the JVM does internally, you know, changes its mind left and right. And as far as I know, no one's published any work on that in, you know, decade or 20 years. I haven't seen anything come around. Sorry, baby pictures with a teddy bear and flowers I sent. Never mind. Grandpa again. Not again, I'm sorry. Grandpa still. Enjoying the grandpa thing from remote. And the other bit of, you know, non-news is that I'm growing a mullet because I haven't cut my hair and, you know, I have the COVID haircut. I've trimmed my front several times and my back is getting longer and longer and I need a haircut. Fine. Does that answer your question? And if Jordan, if you want to go down the next step, you know, the next is just all detail work. It's like I have so many registers, I have so many hardware ops, I have so many this and that, and kind of divvy things up. Give some to this guy and some to that guy. Is that, I mean, are you?
I'm not in the process of designing an ABI, but I've been looking at the different C ABIs for a while now. So I was wondering if anybody else had any thoughts. For instance, the Windows ABI and the sysv ABI are wildly different as far as complexity goes. The Windows ABI just fits everything into a 64-bit register. So that makes it very simple. If you need to do some kind of transformation, it's all one-to-one. Whereas for sysv, for instance, if you pass a struct that doesn't fit into a register, it will try to split the struct into multiple registers. And that if you're implementing native interrupt, that makes things a lot more complex. And you have to look into these struct definitions recursively to find out if things are being passed into integer or float registers, and it becomes very complex. And I'm kind of wondering, is this something that people just thought, hey, that's cool, let's do that, kind of PhD research papery, or?
No, it was micro optimization. It was,
yeah.
Hey, can't we make this go faster? Somebody somewhere down the line 20 years ago got frustrated because clearly you could send it in a register and clearly it was not, and clearly there was an overhead that he didn't want to pay. So he got, you know, fuck it, I'm going to go fix this. Right?
Yeah. But what, I wonder, what's the overhead though? Do you know between the two?
Oh, well, that cost has changed. That's what I was talking about. If you get a more modern processor, the cost is a lot lower. The difference. The packing into registers of subparts of a struct typically turns into a couple of register moves, ands or shuffles, which are on an x86 execute at 2 to 4 clock cycle, like a fractional clock cycle. And probably some count of those values are in registers already. So that's what your cost is to pack it. Your cost to store it down these days is a clock per store, and then a clock per load to pull it back up. And that didn't used to be such a low cost because those guys would happily conflict unless you had sort of a more advanced store buffer technology, but nowadays most folks do. So, you know, you're talking at a call site that I'm returning a struct that's a little large and a little complicated. The return takes me 2 clocks of register shuffle plus the return costs and the argument, say, restore costs, versus 4 clocks, of which 2 are stores on the caller side and 2 are loads on the callee side, or the vice versa or whatever, plus the other overheads of making the call, times the frequency I do the call. So it's not very big anymore. There was a time when I would do the store in one cache line and the load on the same cache line that happened at the return point would block until the store could get the cache line in the L1 cache, which would typically have to drain your store buffer while other ops were still in process, which would typically add 5 to 10 clock cycles. And the cost was triple, quadruple what it is now. Now x86 is pretty aggressive about doing, you don't alias load store bypass in the store buffer. And it's been that way for a while. And that's specifically because it came with few registers, so everyone spilled the stack. So there were all these stack conflict, stack aliasing ops that were going on. But x86 basically knew that it was the stack, and so you could take sort of TD rules on how to bypass, and no one would care or catch them at it. And so he put the hardware in to do that, and then, you know, they just click off, click, 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 1 per store, 1 per load.
Yeah, makes sense. I think you have to always shuffle, right? Because you need to maintain by value semantics. You need to always do a copy, right?
It depends on what people are doing. You know, Java only passes primitives and pointers, no structs. So they're by value semantics all the time, and that's just normal. C would normally do that, but you can ask for by value semantics. And then you get the copy, which in some contexts is worthwhile, but very specific ones, because the overhead of maintaining a copy of a large thing quickly exceeds the cost of, you know, the performance cost of putting one down in a heap somewhere and leaving it, passing a pointer. Right, if you have a memory engineering costs to track the lifetime, that becomes a pain in the butt. And so maybe you want to pass it by value for that reason. If you're looking for performance, if you're passing around like complex or point, so small things that are very, very common, you can pass by value. And, you know, doing graphics, I'm passing points, and it's a freaking byte per point for RBG or whatever, X and Y. It's, you know, it's 2 bytes for X and Y. I'd rather shove it all in a register and declare the struct in registered and take the slide left, slide right mask operations as opposed to loads and stores. Yeah,
in my case, we don't write the C code, right? So we just have to support anything that anybody might want to do in terms of C API. So
I say, no, you're calling from Java to C. You only have to support those things that Java can do when he calls to C. In particular, Java will never pass a struct in registers.
Well, we're doing that now, so.
You're passing structs in registers.
Yeah. So the structs are just in off-heap chunks, and then we copy them to registers when doing the call.
Okay, so there's some Java syntax you have that lets you define a struct that you're going to pass to a native call.
Not a syntax, it's an API.
It's a reg, you're supporting reg call, or?
Yeah, how do I actually invoke this call from Java since I have no way to define passing a struct in Java?
We use a memory segment, which is basically just an abstraction over an off-heap chunk of memory. And then attached to that, we have more or less a memory layout that describes the layout of the struct, and it has all the ABI information in there.
I guess I'm asking, why are you bothering, since I can't do this from Java directly, but I'm asking Java to very carefully, very complexly line up. You're trying to call some random piece of native code from Java, no matter what that native code ABI is?
Yeah, no, it has to be the C ABI, but anything that you can find in a C shared library, we want to support.
Would there be an intersection with Valhalla in passing complex types by value?
Maybe. I'm not super up to date on Valhalla, but they, as far as I understand, they also do something with calling conventions, passing structs or objects into multiple registers. But it's a little bit different there, I believe, because they use scalar replacement a lot. So you kind of lose the view of the entire object anyways.
I thought they like took the C code and
Yeah, like I said, I'm not really up to date on Valhalla.
All right, fine. So if you're willing to go down the path of being more of a VM engineer, the hack I did at Azul here like makes this all go away super easy. And that's, I wrote a piece of code that would given two signatures, Java or native of either side, left and right, it would write a wrapper chunk that would do the argument shuffle in place, on the stack in place, and just exit with the shuffle complete.
Yeah, that's basically what we do. So we have a method type, which is from the method handle API that describes the Java side. And then we have something called a function descriptor, which is basically a tuple of these memory layout objects. And that has all the ABI information embedded into it. So we derive the linkage from that. And then we have some stub that does the shuffling.
Yeah, okay. And then you cache them because they're all invariant across signatures. And most signatures are really common. There's a handful of very common signatures.
Yeah.
Yeah. I think when I did this work at Azul, it was like there were 20 signatures that were really common, and there were 150 to 200 ever total signatures in any large Java application, and that was it. So it was very.
Currently, we actually only have one stub in the quote unquote interpreted mode, which is just copying all the argument registers. And then there's a pointer to the stack and then a number of stack bytes that it needs to copy. But basically, we only have one stub for any call. And then the intensification will specialize that. But that might change in the future.
Yeah. Okay.
Are there issues, Join, when you're calling out with respect to the C code, examining the stack, making assumptions about, for example, exceptions and things like that?
There are, whether he knows it or not.
Exceptions, you mean like OS exceptions or?
Well, that's kind of open-ended, but I'm thinking, for example, C++ exceptions and so on.
Yeah, we haven't really started looking into that yet. So for now, it's just C.
There are two obvious cases to handle: Stack Overflow and somebody threw an exception and you have to unwind. Very different notions here.
Yeah, we're still looking into that, I guess.
Okay. I would claim
it's still very much a prototype.
That those are both very difficult and will drive your design choices, and you should tackle them first and not last. Because the ABI shuffle of registers is sort of understood. It can be done, even if the specifics might vary or get complicated because of struct split, blah, blah, blah. But Stack Overflow and being efficient is a tricky bit to get right. It's not hard. I mean, it's not expensive or can be cheap, but it's tricky to get it fucking right. And to do that, you have to understand how the JVM intercepts Stack Overflow and then gets to a safe point while it's typically in the middle of executing a foreign function call. And then, and then there's people talking about in chat here, Matt, exceptions getting thrown in the native code, and you have to unwind the stack and do something with the native exception. Both of those are Stack Overflow and that one are both very tricky to handle right. Need to do something with it.
I think Stack Overflow just goes to the JVM signal handler. and then we get a crash, right?
No, you're close. The tricky part is the JVM has to get to a safe point and has to be able to describe the stack to get to a safe point. So at different times, it's been, I have to probe ahead in the stack. If my stack frame is bigger than X, I have to probe. And then when the probe throws an exception, there's a bit flip somewhere that says, run forward the least amount of work possible to hit a safe point, then stop at the safe point. And then you inspect and say, oh, it's Stack Overflow, and now I'm at a safe point, so I can unwind. But that doesn't work so easily on native code. And if you're in the middle of constructing a stack frame, when you first touch a new page of stack, you might not have a convenient place for the VM to be able to inspect and find return address that it could then declare what the last really valid stack frame was and begin unwinding. So you need to understand how that works to make sure you're not blowing it. One of the rules was if I was going to be more than 4K ahead, I had to probe it first. And another rule was I had to have a return address in a known place such that the exception, when it happened, could inspect and get it. And I had to have that right away. So you had funny rules when you started doing register passing and register unwinding about when and where the return address got plunked down and when and where you bump the stack pointer. So I'm not saying that's hard to get right, but it is, I'm sorry, it's not expensive when it's right, but it's hard to get it right.
I'm not really sure what the difference with JNI would be. I'm not sure. We're not throwing Java exceptions from native code, right? It's just...
what I'm saying is go immediately write the test case that runs your stack to within a fraction of an inch of out of stack, and then make your native call and see if you get a Java Stack Overflow exception or you get a crash and burn.
Should be crash and burn, I think.
No, it should be stop a Stack Overflow exception. At least that's what it has been for the last 25 years.
That's surprising. Usually when we're native code, we get a crash and burn.
Okay, that was working, and it was working at Azul and working at Sun. Maybe it's given up on, people say, no, I don't care. No, and then the other one is the unwind through, which is the native throws a structured exception, or you have a native frame on the stack, but you called into Java code, and then the Java code barfed and wants to throw an exception, including Stack Overflow, and wants to unwind all the way out through the native frame.
Yeah.
And
I don't think that is working currently.
I'm sorry, that is working.
That is not working currently.
I would stare hard at why that's not working, because that will change how your calling convention is generated. And it may be, and it's a lot easier to get it right first, and then figure out all the different little corner cases of the exception. Like, you want to call all these other corner cases? No, fucking call square root or POW, something stupidly simple, and then test unwinding through these things.
Yeah.
Because these are hard to get right, but once you get them right, you can keep them right while you add, hey, I want to have half struct split between registers and floating point and SSE, and God knows how complicated they got. But
so
get the overflow.
The problem is getting the unwinding right, basically, is what you're saying.
Yeah, the unwinding is a bitch to get it right first.
Yeah. And
then fill out all the, because you can start with the thing that says, we'll cover all the following calling conventions and we won't handle split struct, blah, 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 and we'll just throw out at you and say, sorry, you can't call.
Yeah, okay.
And then you can lazily fill in all those bits and pieces. But yeah, if you can't handle, I threw an exception with a native frame in the middle, too much code would die there.
So Matt posted something in the chat. Matt, you want to talk about how Linux is quite different? Because I remember something from when I was using the POSIX coroutine support for the year or two. It was in POSIX. And I remember some pretty serious issues on Linux trying to call Linux kernel calls from a fiber.
So exception handling support for Windows and for Linux on the native side, that is C++, looks very, very different. I know that LLVM started only supporting Linux, and later on when the Windows support was being added, it actually took quite a lot of work to support Windows. C++ exception handling as well. It's already very different starting from the way the code is lowered. In C++ Windows, exceptions are basically funtlets, which are like small functions you can call with what you throw from one stack frame as you go, and unwind is passed as if it was an argument to a function, basically. And it's generally, you needed all of that support. You can also on Windows do tricks like convert operating system exception into a C++ exception and handle that on the C++ side, which is entirely new. So support for that also had to be implemented. So in general, excuse me, in general, it may be a good idea to implement both at the same time, because retrofitting may take quite a lot of work and it may be a bit painful.
Does LLVM now do that for you?
Yeah, it supports it now, yeah. There's been a few talks on that, actually, pretty interesting.
Yet another reason to use LLVM.
Yeah.
And Azul switched to LLVM as well, right?
Well, we use LLVM for final tier compilation. Yeah.
So what are you using for JITs then? LLVM, are you using C2 still? Or you have it as a tiered thing?
So it is currently deprecated. We still have it in the source code. It's still available under flag, but it's not tiered with LLVM. It's either C2 as final tier or LLVM as final tier.
So still using, is it still using C1 as a starter tier?
Yeah, it's so fast and it does the job just well.
It does the job. Yep. Yep. Well, that's it. We're done. I don't know. Cameron was poking me about AA and the exception handling is a silencing effect. Yeah, I haven't thought through what I'm doing with exceptions in AA, so that's a good conversation. I have this theory that says most of the exception handlers I've ever seen in Java suck really, really badly, and they're never tested. And because they're never tested, I can tell because they would just croak and die if they were. But also they're commonly in places where you can't possibly do recovery from. They commonly log it verbosely, and then they remove some fraction of stack and throw again, typically loosening the exception so it makes it up to the higher layers, who then catch it, can't do anything with it, print again, lose some more layers and throw again. So you get repeated stacks, frames printed out, and all contents of stacks like sliced off. So when the final guy gets a chance of actually catching it, he doesn't have the information he needs to catch it. Whereas if they had failed to catch it and just let it propagate up, you'd get a clean stack trace and a clean chance of error recovery. So my current theory says you can throw an exception for obvious reasons. So range check is an obvious one that I'm not ever going to be able to type analyze my way out of. You can see an exception go by and do whatever recovery logic you want, but you're not allowed to trim the exception unless you declare that you're going to handle it completely. And if you handle it completely, the exception is completely removed and you're not allowed to throw. That is to say, you must recover if you're going to declare you're recovering. And if you're not recovering, you cannot remove information from the stack throw, but you can do localized recovery and then go again.
So is that the AA recovery model?
That's my current theory, and I haven't tried it in practice, so I don't know.
12 steps?
Yeah, to alcoholic anonymous recovery, yeah. But they're like, I'm running a web server, I'm running arbitrary code. If one of my handlers has choked, I'm willing to catch, throw the handler away, and go again. and I can do full recovery at that level. If I'm doing file operations, I should be handling the basic file fails, file not found, security blown, disk full, whatever, all the basic shit I should just handle at some local low level, and that shouldn't propagate very far. But no one should have the right, like if someone wants to throw a file not found exception and someone else like hates it and they don't want to deal with recovery in Java, they rename it to a runtime exception, possibly losing some key bits along the way, and throw it again. And then, oh, it's runtime exception. So it just propagates up as that. And then some high level thing just has no clue what the hell happened. And I've saw dozens and dozens of these things where the handlers just threw away the precise exception because they didn't want to deal, but they couldn't handle it. And they shouldn't have ever bothered to catch it and rename it. And the other layer shouldn't have ever bothered to say, and I'll take a file not found and 27 other exceptions that I don't know what to do with because I'm not going to handle them either. Until you get up to a point where you're actually going to catch and handle. So I don't know what the real right answer is, but I know what Java does can be improved on.
Is that a side effect of them being? Is that a side effect of them being checked exceptions?
There's a checked exception piece which says I don't want to deal, so I catch it and rename it, typically throwing away some crucial information along the way. Also, typically logging it verbosely when in fact someone else is going to handle it nicely, and your log file just gets spewed. There's a separate issue I have with logging, excessive logging depth, but that's a different one. But yeah, there's a checked exception fail. I don't know what the right answer is, but I think maybe having a bunch of things that are exceptions not be exceptions and demand that you handle them. And if you want to throw instead of handle them, I'm okay, but you have to say I'm going to throw, and then somebody else is going to recover. And the recovery, it has to be a real recovery. It can't be I don't know what to do, so I'm going to hide it recovery. That's not a recovery.
I think part of the...
Isn't what you describe a normal and healthy process of abstracting things? And if like some library doesn't want to tell all the details what happened, just say, well, I failed to do what you asked.
That's a full recovery because the state for the library is I return an error or I return a value of some kind. So I return this thing that has, I didn't do it. That's a full recovery, and that turns the exceptional state into a state machine answer kind of state, which is fine. The library's, in theory, the library's not dead anymore. It's alive and well. There's no internal confusion. It's not blowed up in any way, but it just said no, and I carry on.
So you're saying it would be cleaner if the library, instead of throwing just some generic exception, would explicitly return fail state and like.
Yeah, right. So this is really common. I return you an OK flag and the value you want, or return you an error flag and perhaps a string. Right, so some conditional thing, and you have to deal with that. You can get an error out of this library, but it went from an exception. So suppose I demand that you take an error out of every possible thing, must return an error or an OK and a value or an error thing. Suddenly your code gets populated with, I have to test for error at every layer, every step of the way, and do something every time. Well, this makes for very robust coding and very verbose. So the whole point of exception throws is I don't want to do that.
We call it Go.
It happens in other languages as well. Go is not the only victim here, but I've seen
it just is the ugliest.
Yeah, okay. So I want to have an exception to not have to do that. But at points, I want to say, especially at abstraction boundaries like libraries, I want to say, you're not throwing out of the library, you're going to return this error state. And if I call the library, I have to deal with it at the library point. But in my own internal code, I can use an exception to get the fuck out. And then at my boundary, which called this library, at my boundary, I have the same catch and said, I didn't do it, I don't know why, I fail. I clean up and I fail, and I tell you, nope.
Well, semantically, it's equivalent. Like you can define the API of the library that, okay, instead of returning an error, I would throw this exception. Will the explicit return of like failure be clearer? Maybe, yeah, that makes sense. But I think it is equivalent on the grand scheme of things.
Right, I'm looking for convenience and clarity.
Okay.
having it such that if I return an error and you don't want to deal, there's some very short syntax that says, and if it's an error, test for error, and if an error, throw again.
But there's a difference between an error and an exception, and I think this is where most people just completely lose the thread.
I'll agree.
An error is not exceptional. There are errors all the time. An exception says this is something that basically shouldn't happen. If this happens, like
I'm fucked, and I don't know what to do. Yeah, I agree totally. File not found is not an exception; it's an error.
Well, it's only an exception if it occurs in some place where the file has to exist.
Yes.
Right? Like where it's like, I guarantee this file is going to exist, so go do the following thing. And it's like, wait, your guarantee. So basically an exception only occurs when a guarantee is void.
So the guarantee is not really a guarantee. Same as, range check out of bounds. Instead, there's something that says, my expectation is this not being present is such a rare event, I don't want to deal.
There is also the connection with I think what Cameron said about guarantees and API design and out-of-range errors. So say, to specify the terms, what I mean, consider function like binary search. You know that the precondition for you to call this function on a collection is that you would like the elements to be sorted. This is a precondition of this function. It may be either fulfilled or not, but the function can only work if that precondition is fulfilled. You wouldn't necessarily check that. You wouldn't go and compare the entire collection to see if it is sorted each and every time you call your binary search, because then your check and potential whether you want decision whether you want to throw exception or not would be linear, even though the binary search is supposed to be logarithmic. So that would be pretty bad idea. And now there is a common criticism now in C++ that there is a container, which is the main container in C++ called std vector or standard vector, which is basically a dynamically sized array. There are two ways to access elements in that vector. Either use the operator subscript, which is the brackets operator when you give the element index and you retrieve the element or not, or you use the @member function, or in Java term it would be @method. And that function is a bit strange, and that is widely criticized. And this is very much against the design of vast majority of C++ libraries, because the strange exotic thing that this function can do is that if you give it an index, which is out of bounds, this function can actually throw an out-of-range exception, which is wild if you think about this, because now you are introducing very expensive checking for the inbounds, a little bit similar to how binary search would be checking its precondition and throwing exception if the collection was sorted, even though this is not the contract of the function. So from the API design, you have now widened the contract to the maximum possible collection of no preconditions whatsoever. Because now basically, if you are saying, if you have defined behavior for the function to throw exception when the index given is out of bounds, now this is defined behavior. Now you are stuck with this forever. You have to support it. You can never change it because customers will rely on this in C++ applications. So you cannot now say that the precondition of the function is index is invalid range, because it's no longer the case. Add has to work completely entirely without any preconditions whatsoever. And from the design point of view, I think this is problematic, because this is basically a corner you cannot ever get out of. Now,
this is array list, and the call and array list throws you an out of bounds. Same exact story. So
exactly. So this is also no precondition contract effectively. It is it's as if the binary search was basically checking the sortedness precondition.
Right. And I am okay with in effect, a managed runtime gives you the whole no preconditions, because you're guaranteed some sort of safe behavior at every step of the way. But that safe behavior may not be the behavior you want. You may not want to pay the cost for it, but you get a guaranteed behavior. That was the big step up from Java to C, was the guaranteed behavior on out of bounds.
Exactly. Of course, now it's impossible to opt out. But of course, putting this in the standard is a problem, because now we cannot opt out of this the other way around. So the pragmatic way that it is treated right now is to have the usual operator subscript access, and this one has the precondition of the valid inbounds index. However, if you want to have audit built, then you essentially build with sanitizers, which is something that has to be done on a daily basis anyway. If you have continuous integration system, for example, then you always have a build of C++ with sanitizers, and preferably fastest build as well. And that usually catches a lot of memory errors. But from the design point of view, it is a decision. There are, of course, different trade-offs, but it is a decision that you cannot essentially get out of. Once you define it, you cannot revert it, because then you would be breaking people.
So I'm okay with range checks because I think Java proved their cost can be acceptable. Whereas the exception costs have always been, building a stack frame, a stack trace has always been expensive, very useful for debugging, very expensive to build and throw away. And so the spec that says I built or I didn't build a stack frame, I think does need to be thought through carefully. And then in my head, the limit between, or the line between error and exception is I got a stack trace expensively with an exception, and I didn't with error. Error is, I called an OS routine for doing a file open, and I got a byte back that said, here's your error code. And it says E not found, E no F, or whatever the hell the fucking thing is. And that was super cheap. And I could go kinds of recovery.
What are you going to do for your language for out of bounds mistakes?
I'm going to throw an exception.
Together with the full backtrace?
With a backtrace.
Okay.
With my expectation that this is a crashing situation, you'll want that backtrace for debugging purposes only. If you would rather have an error back for an out of bounds thing, I might hand the C version, if you will. Well, not C version, it's just a managed runtime. So you either get a stack trace and a throw, or there's another version that says, I hand you back an error or success code somehow. The obvious error or success is that I actually fold them together and say you get a null back if you're out of bounds, which conflates, obviously, if you have a null array, and I can't tell the difference. But I think the count of people that want to do an array operation where they're okay with it being out of bounds and they'll handle it getting back some sort of flag saying I'm in or out. I've tried that coding style and it sucks. I've worked with a managed runtime where out of bounds didn't throw an exception, it just returned you a value.
Oh no, that's the worst. I think we can agree that that's the worst.
Okay, fine. So then with throw an exception. Yeah.
That's impossible to debug. That I think.
Yeah.
There are no advantages to the style I can think of.
Yes, if I accidentally went out of bounds, it was a nightmare. The usual case was I just never went out of bounds because I had the correct precondition, but I had to write in the code handling for teaching it that no error was happening here. So if an error happens here, I had to mutate the error into some other thing. Like I had a collection of never possible to happen errors that the language demanded I hand support for. So I had a whole lot of error handling written. This is Elm, but there's versions of this floating around where I had to have error handling for errors that could never happen. And that was verbose and painful to like move them off to the side so I didn't have to deal with them. No, I'll throw an exception if you're out of bounds, totally.
What work did you do with Elm?
Oh, I did a bunch of stuff with front ends. So big data financial modeling, financial viewing, both for stock market fraud and for my own personal, stock market prediction stuff. 30 years of stock ticker data, dozens and dozens of analyses overlaid over the raw data, and you could zoom, pan, scroll, in and out, turn on and off all kinds of analyses. That was all in Elm. I guess that I used not D3, there's the other one, Dynagraph for the actual presentation, for the graphing layer, but I fed Dynagraph from Elm for all the GUI operations, including pan, scroll, zoom, on and off, all your different analyses. Honestly, I fed the data from H2O, which did the analysis crunching, in H2's compressed format to the browser in compressed format in Elm. So Elm dealt with raw byte arrays that were compressed data and unpacked them for Dynatrace on demand to keep the volume low. So I could put in, I put in 1 million points in a browser without any trouble. Whereas the current extant things that I've seen people do could say at 100,000, most browsers are choking to death. So I could get 10x that. I could probably get to 10 million with a little more effort on the compression side before the browser got choked on it. But the secret there was I didn't expand the data except in Dynagraph. So Elm was doing data decompression on the fly, byte by byte or pixel by pixel or something. It was reasonable. So I did a lot of fun stuff there. And then I did some games with Elm, and I did, what was the other major thing I did? I did another major project in Elm. It's fine. So I did a bunch of stuff there as a presentation alternative, like think, you know, the React Manifesto. Elm sort of took it to the next level with functional programming all the way. It was really nice for that piece. The error handling was both a pain in the butt and really good, both good and bad. It forced you to handle every possible thing as an error inline. That was a pain in the butt. The upside was once you got past the compiler, your page typically just worked. So the overall coding development cycle was probably faster than doing the same thing in JavaScript, but you had a more of a think ahead effort they had to go through. I don't know. And then like certain kinds of raw bit math were total fucking pain in the neck for no good reason. And so I would never do that again. Like you could not write a random number generator in Elm to save your soul because you couldn't do bit twiddly things worth a spit. There were some things that it did, you know, it had this closure style, incrementally modified invariant, what do you call it, data structures that are all invariant, but you incrementally tweak them and add increments, but the old copies are
persistent data structures.
Yeah, I had persistent data structures everywhere, which are way too slow for the big data. So I had to just sidestep them entirely for lots of things. For the actual pan, scroll, zoom widgets on the screen where you're clicking through. Oh, I did this for an IoT play doing location services, dynamic location services for thousands of things at a second by second granularity over a factory floor. Again, a whole lot of widget buttons for selecting and scrolling and panning and filtering and this and that. And that all works great. And for the big data piece, you had to, you know, step away from the Elm. It was too slow. So there was a use for both pieces. And so there's some thinking in my heads about, you know, how do I keep the reactive style behaviors that you want, because that's a very good coding style, in my opinion. It's very useful, very functional, very working, works well for doing asynchronous reactive coding. And all the immutable persistent data structures like suck for performance as the scale grows. And so what I want for persistence and the browser management of the GUI state is pretty small. That's all great. What I want for persistence when I'm streaming 1,000 things from a factory floor at a rate of, you know, once a second, and I'm looking at 6 months worth of data, I got millions to billions of points. I'm not putting those in any persistent data structure right now, not the way they're designed right now. So they had to have a different, both paradigms were useful, but they were in different places and you needed to deal with them both. And I don't know what the right answer is. So I'm screwing around. AA came around for a variety of reasons. That learning was one of them. The other one was doing data science in Java sort of sucked, except I had scale data. So doing data science on, you know, millions and billions of points in Python and R sucked for performance. Doing it in Java sucked because Java sucks for doing data science because it doesn't have the right dynamicism in the right places. So then I headed off into doing AA and said, I'm tired of implementing somebody else's language. I'm going to implement my own, damn it. It's getting there. I don't know. I have all kinds of fun other stuff going on with it all at the same time that I think are very useful and very, it's tiny in terms of the core language, but I can do everything from a very, very simple syntax. So we shall see. I'm sorting out flow analyses for final fields, which I think will be very similar to flow analyses for Rust style memory management, linear logic tracking through first-class functional languages. I think I'm going to get there. Oh, Matt threw out a question. What's NPX?
So that's, go ahead.
No, go ahead.
So that's Intel Memory Protection Extension, which is now deprecated. It allows you to do bounds checking. It had instructions for checking lower bound and upper bound for effectively spatial memory safety to make sure you are not violating memory access before the bounds of an array or after.
Isn't that, okay, is a bounds instruction? There was an old bound instruction.
The bounds checking instructions essentially,
Yeah.
with a few extra helpful tidbits, but I just read it. I got curious why it got deprecated, and it turns out that it was actually not that good compared to address sanitizer, and it had very large overhead even compared to software-based bounds checking, so that explains it.
The JIT does a good job of removing bounds checks where it counts. So Azul had bounds checking hardware, but sort of very minimalistic. The array length had to be in a register, and the base of the array was in a register, and the index was a register, and that was your 3 registers.
I know. Let's do a new extension and call it segments, where we would access.
Yeah, well, Intel went down there a long time. Well, that segments were processes. That was for process-based bounds. That was not for array, the fine granularity of array bounds. That was for process bounds.
Well,
But can you imagine?
Because what process would need more than 64K?
There you go. On the flip side, Bill Gates is like richer than I am.
No, that was 640. I'm talking 64.
It could be, yeah. Yeah,
because
right.
SSBP was so you could have you had DS. ES wasn't even there at the time, so you had DS, SS, CS,
DS for code,
CSIP. So yeah, and one more. So you basically had 4. Oh, maybe you did have ES. It was.
I thought you had ES.
Yes, you had ES. It was so right. So
that gives you
SS, CS. So code, segment, data, and your destination.
Your stack,
data.
code, data, and extra.
Yeah, extra was your destination for copies.
Yes.
So you had 4 up to 256 kilobytes of memory, which is what the 286 supported originally.
Yeah. I coded in assembly on those machines. I'm well aware.
Now it's for the thread locals. I think both Windows and Linux. One is FS, the other one is GS.
Right, FS and GS came later.
Right.
Yeah. And what you can do, right? Life goes on.
So I was going to ask an opinion question on the error topic, while it was open, but we went off on some tangents. But I was curious if the lack of being able to return more than one value is the reason why so many people abuse exceptions so much, right?
The Elm solution was you return more than one value, you put a pair. It's the error, comma, string, or OK as a flag in enum, and a type tagged union. And that worked out really well as far as I'm concerned.
Go to something very similar, right?
Yeah. So I claim that works out well. And the overhead is up to the jet. So this is all syntax overhead in the language. It's no performance overhead. It's syntax overhead. Performance is all what the JIT does. So AA will totally take a return of a anonymous localized struct and unpack it on the other side with the obvious unpacking syntax. And I'll just assume the JIT turns that into something sensible for performance.
There is a proposal for C++ for low-cost deterministic exceptions that actually supports to do just that, to reuse the register or even just a flag bit in the registers on x86. And that essentially is producing several return values out of a function. You just provide some of them out of band, like when you use the flags register. So this could be interesting. It had pretty good empirical results. It reduced the C++ exception handling costs by something like 80%. So this could be promising.
Yeah, the best way to reduce C++ exception cost is to avoid using exceptions in C++.
That is what LLVM does.
That holds true for Java as well. I think that the theme here is that exceptions should be exceptional and not the common case.
The other point I was going to say earlier, Cliff, you were talking about stack traces and about the concern about generating stack traces. But if you analyze stack traces by the billions, I don't mean by the thousands, I mean by the billions, you'll see that there are only about 5 of them. And what I mean by that is that, and Kirk, you probably can chime in here,
I know what
but
you
you'll
mean.
notice there are dramatic patterns. So you might have variation at the leaf. You may have iteration within it, so recursion from the programmer's point of view, but it's iteration within the stack trace itself. So there are patterns in there, and you can literally cache. And I'm really surprised Java doesn't do this. You can cache most of that and basically build a backwards unidirectional linked list instead of putting together, you know, multi-kilobyte, multi-megabyte sometimes stack trace.
So, okay, so Azul went down this path of low overhead profiling with stack traces. Along the way, we hacked the runtime such that we could guaranteed collect a stack trace at every possible point at very low overhead. And that partly that was we knew the stack pointer and the return PC value had a fixed known setup, and those were always guaranteed in place. So that when you took an exception, you could immediately grab stack pointer, return address, hash for the length, and go again at very low cost. And we would collect 8 deep stack traces on a timer interrupt 1,000 times a second. So yeah, we would get millions and billions of stack traces, but only at 8 deep for the profiler. And then immediately, as you point out, there's bazillions of common ones. If I'm looking at a general purpose stack trace, unless I do some sort of knowledge about where I have last unwound the stack since the last time I did something, this is what garbage collectors play, the short stack frame lookup, whatever, over kind of game. Unless I play that game, I have to, as a minimum, I have to crawl the stack and grab all the parts so I can go hash up and look for commonalities. But yeah, I'll totally agree with you. There's a huge amount of commonalities. And if I hash a thing up on some temp storage I've set aside permanently, like in thread local, then I don't actually do any allocation. I just grab my thread local space, I build a frame, I do a hash, I get a hit from this point and up is a hit and this point below is not. I move the below off into the heap and leave the hit as a linked list, and I return and I'm done. Yeah, that's been in my thinking all along. Not that I've got there.
Yeah, we hit this problem in design because we had asynchronous fibers where one fiber calls into something which creates a new fiber, and that calls back. So you have kind of reentrancy into a previous domain, which creates a new fiber. And then if there's an exception, you actually want to see that you called over there and it called over back over here, and you want to see that. You want to see those.
So are you trying to get an exception to help you diagnose your fiber layout? Or are you trying to get an exception to
No,
hand?
this is for developers. This isn't for us. This is.
Okay, yeah.
So
because
if
at
they
H2O,
throw,
I did exceptions that were crossing the cluster.
right.
So this guy called this out to the giant mob with cluster. Somebody threw an exception, but usually if one guy threw an exception, they all threw it. Every core, every processor threw it, and they threw it 1,000 times in a row. Because they grabbed every piece of work from the fork join list. They all died the same way. And all these exceptions come flowing back. So I had to do all kind of unioning of them. And then I crossed boundaries in the cluster boundary, but
Same
I made
idea.
it look like a fork join split point and just unwound it. And I said, and here is an exception. Here is a sample stack trace. And I had 120,000 of these. That was what you got as a report.
And the challenge is that the caller has since gone on and done something else. So if you don't actually save this, if you don't actually
I
save
saved
the stack,
them until the caller did a join point, and they collected on the join point by the millions, and not by billions, but
right.
but it could be by millions. And then at some point I declared this was a fixed point where I'm no longer doing parallel. I stopped here and I said, do a parallel thing, and then I joined back. At that point, I threw a normal Java stack trace in one thread that would go to your debugger, but the trace itself would leap through the cluster.
Yep.
And also have a report that said, and also there were a million more of these.
Right. So did you actually have to throw an exception to generate that stack trace?
Yeah, and I caught it.
Wow.
No,
So
you don't
pretty...
have to throw an exception. There's some call
Yeah.
you do to get an exception.
Same.
Typically, the first level exception was the standard one that Java threw, because I wasn't expecting it, right? I wrote some freaking broken array math code. It threw an array index out of bounds exception somewhere. It went through the fork join handler, which caught it at some point and said, okay, we're gonna unwind and quit throwing tasks, but he's already launched 50 bazillion of these tasks, so 50 bazillion throw back at you. And he started collecting them. I had a collection point where I looked and said, this looks close enough. I'm going to declare identical, keep one, and run by counter instead of keeping the other. And I kept actually like the top 3 or 4, I kept a collection of them because you got a couple different varieties of failures typically when you had a fail like that. But there was usually a dominant one, fine. Then that was the result of that fork join on a node, who then gathered up that pile as the return value and sent it over the wire to the other guy, who then took it back as, I either got an okay or an error. If it was an error, I had this stack trace wide and counts and whatever. And if it was an okay, I typically had a bit saying it was good, the roll up bits, and all the big data had their updates updated, and that didn't come back, obviously. But and then he rolled that up again recursively until you got back to your main launch point.
So we have, we have the equivalent of basically millions of those happening. So we didn't want to be generating an actual stack trace for millions of calls.
Right. I had them generated by the JVM for me, but I quit forking as soon as I started seeing the fail. But I had already forked many, so I got lots.
The idea we had in the design is that basically, if the caller wants to continue asynchronously after issuing the asynchronous call, if it wants to continue, it'll basically lose its point to generate that stack trace. So it has to basically register where it was, and then you can cache that information, because it's going to happen a billion times.
Right. So there were sort of 2 broadly done parallelism things in H2O. One of them was strictly fork join. So basically tree-based, deterministic roll-up order, but things could execute out of order and they would just hold on to their state until the roll-up point came. So that was very sweet when the roll-up was in order, because your roll-ups could also throw exceptions. And that one had a very deterministic roll-up, so you got the exceptions deterministically, and it was easy. The other one was exactly asynchronous. There was no tree structure to it. You did whatever you did. And we just moved the exception along until you joined. And then we would look at the exceptions from the joiner and the joinee. And if only one of them had an exception, that was the winner. And if there were 2 and they're identical, the count. And if they were not identical, up to some reference of identical, we kept one and said, and there were others, and kept going. But you never lost an exception. And we only threw, and we didn't track your points like you were talking about. If you forked away, you lost where you came from. And we didn't have the callback with fibres calling into themselves that we would track that way. It could happen. Guess it could happen. Maybe we did get those. We took whatever Java exception as the leaf exception, and then we just stitched them. When you added somebody else who called, you could get a stitching effect, and particular over cluster boundaries. That was definitely happening.
Yep.
Yeah. There's a thing there, and I don't know that we ever said we call the manual stack trace maker, and I don't know, like I think we didn't, or it was very rare, and we didn't carry on with and I was here bit, and I moved on. So if I got an exception, I could tell that happened. So that information was lost. So if you're doing the async model and looking at exceptions on the async model, it was harder to debug.
Yeah. The other thing, Kirk, if you're listening, I have actually seen several different applications in production that spent well over 90% of their time filling out stack traces. Mostly that just was being piped into logs, to your earlier comment.
Yeah, yeah.
So have I.
I've seen that too.
Yeah,
Ugly.
it's amazing how you can be a hero with stuff like that. You know, it's like, you know, you have a null pointer exception here. If you fix it, your application will run 45 times as fast.
In one case, I saw exception handling actually being used for flow control. So it was quite intentionally done. And this was in an HFT framework. Yes, exactly. What?
Most of those guys that I talked to, they were like poison on exceptions. Oh my God, that was a firing offense. You'd get shot.
Well, it was an easy find.
Yeah, yeah. Yeah, anything that's doing that on a regular basis, that's going to be an easy find.
Did you hear the story about the company that set all their references to null in object finalizers to help out the GC?
I've seen that too, yeah. That's very old. Or at least I saw that first a very long time ago. I was still at Sun, not Oracle, Sun, when that started coming around. Like, what are you doing?
Yeah.
I'm set to null.
There's all kinds of things that are weird. We call actually we come up with a term with that, call it like tuning by folklore. And
Sorry, my AC just kicked in. Say again?
so we call it tuning by folklore. Right.
That's
So,
a good.
So it's like old advice that no longer applies, or old advice that was never good in the first place, or but generally the word old appears there, right? So yeah, I've seen the nulling out and I go like, seriously? Let's have an explanation as to how this actually works. And you can see how silly this is.
Well, the other one is just simply try it. Well, I tried it 30 years ago on hotspot 1.2. Fine.
Yeah, there's multiple levels of performance optimization, right? First is just thinking about it and thinking, oh, this should be faster, so we go with that. Then there's actually benchmarking and picking the fastest one, and then there's actually looking which code is running a lot and which code is slow, and then trying to optimize that. So with a profiler, for instance. And there's a shocking amount of people who are discussing performance of a piece of code based on pure gut feeling, it seems like.
I see that a lot. I'm with you. And I call it out as soon as I see it.
Yeah.
Quit playing armchair general and whip out a profiler.
Yeah, but actually the benchmarking topic I find is quite interesting because I just had somebody hit me with a whole bunch of results from like parts of the Renaissance benchmark. I was looking at it, it's going like, first thing you're thinking is, who's calling this system GC like every 3 seconds? And they're going like, oh, that's just part of the benchmark.
Yeah.
And I go like, what? And how long are you running the benchmark for? Oh, we're running it for like 30 seconds. I'm like, okay, what? And then you start looking at, there seems to be this rush today towards people building frameworks so they can automatically run whole suites of benchmarks, that they have no idea what these things are doing. They have no idea what these things are trying to, what these benchmarks are actually trying to tell you. They have pretty much no idea if they're working or they're not working. They just know that they just have benchmarks running.
It's also good to run them concurrently on multiple threads so that they finish faster.
Yes, exactly. But so they have this whole slew of benchmarks just sitting there running in an automated framework. So every morning they can publish a report to their management saying like, look, here's our benchmark numbers. And so what does that mean? And the other thing too is I find that, I love JMH, But JMH is a throughput, unthrottled throughput harness, which is applicable to benchmarks where you actually want to do that, which is, I would say, not the majority of benchmarks that you actually run. But every time you present a benchmark to somebody, the first thing you're going to say is like, can you put that into JMH for us? They're going like, well, no, this isn't like a JVM internal engineering task thing where I might actually use this. This is like something else where we actually need to throttle, and then you get into some whole conversations that basically is just measuring throughput, and then no one actually really understands the relationship between throughput and latencies and how unthrottling contributes to latencies because of the, well, you know, the lack of throttling and, you know, how based, you know, queuing and all this other stuff. And it's like, and it's just benchmarking is just a crazy, insane world where it's just more misinformation comes out of there.
Yeah, I'd say performance analysis is a well misinformed world.
No kidding. And it's really kind of bad because we're dealing with groups right now that are doing this type of stuff. And, you know, I think about 6 or 8 months ago, and I say, how long are you running these things for? It's like 30 seconds. And I say, you sure that's long enough? I go, oh, yeah, okay, fine. And just recently they started doing tests and saying, well, what happens if we run it a bit longer? And like, oh, things start changing. And going like, here, try running this benchmark here. Just run it here, turn on the print compilation, and then go away. Like, just go have dinner, have lunch, you know, like, you know, have a nap, whatever. Just, and, you know, like you've been running this thing for 30 seconds and you go like, oh, look at that. 30 minutes out, we still have JIT activity. In other words, we're not even in steady state. Like, sorry, I'm trying not to rant.
It's all right.
I'm trying not to rant. It's hard.
Been an hour and a half.
Unmuting, bye.
And I'm debating, you know, doing other things with my life here. Yeah. That's a separate one. I shoot all databases and all the projects I work on. Never mind, that's a different one. Yeah, so this is good. Let's you know, do this again in a week. I'll put the video.
Yeah, we have an anti-pattern testing anti-pattern for that. That's called data light.
Data. Oh, I see.
Data
yeah, good form.
Yeah, and it's not only it's a data light not only affects the back end, it also affects the harness, right? Because you could put 1 billion records in the database. If you're only ever looking for Mickey Mouse, you've just described your benchmark, right? So you need volumes and veracity of data on the harness just as much as you need volumes and veracity of data on the back end. That's a great paper. What's this one?
You know, there's been a bunch of work showing that VMs actually typically can not get in steady state no matter how long you run them. They're indefinitely running hot and cold, hot and cold.
Oh, okay.
Yeah, exactly.
Modest benchmark code. They cycle performance in some kind of not quite a sine wave indefinitely. And what the hell is that going on? I thought lots of those at Oracle. Sun.
Yeah, we've seen that actually. Oh, yeah, and you get into really funny things too. It's like, you know, I did one engagement where they're coming in and says, hey, you know, like on our hut server, this is running like in 8 milliseconds per transaction, which we're quite happy with, you know, but on our satellites, they're running 25 milliseconds per transaction. And I go like, yeah, cool. This stuff scales up, but it doesn't scale down. And people always forget about the scale down question, right? If you needed to scale down, you actually need to test scale down. And because scale down it's different, and hotspot generally doesn't scale down well. You have to go in and tweak it to get it to scale down. You know, and that's exactly what it was. It was like hot paths were getting their counter values knocked down because they weren't hitting it before the half-life, you know, counters, you know, the half-life rule applied. And that's all it was. And that made a difference of, you know, about 20 milliseconds of runtime. No latency or whatever. So.
Okay, I'm going to try again to close it up here.
Are we leaving? I just got,
been an
I got
hour and a
stuck on a
half. I
call.
got things I'm gonna go do.
Oh, right. Oh, I heard you were a grandfather or something.
I am.
Congratulations.
I have, an infinite number of baby pictures now. So now that you've said the grandfather thing, you have to go see, baby pictures. Let's see. There's a good one.
Okay.
There you go.
Oh, wow. That looks like a baby.
Nice.
There you
nice.
go. Uh-huh.
Oh, yeah, it's very nice. Okay.
And Lisa's in Philadelphia with mom and baby and has been there for 3 weeks, and I'm ready for her to come back. I'm a bachelor.
Yeah.
But
Gotcha.
it's all good. And so I have lots and lots of baby pictures. All right, next week. All right, take care. Bye-bye.
Bye. See you then.
Yeah, bye.
Bye.